Okay, so let's unwind arc length, actually going backwards from the way that it was introduced to you originally, which I think sort of makes more sense. I mean, it's a shame it can't be presented this way the first time around because you don't know what parametrized curves are when you first do arc length, but suppose you did, right? So suppose we've got a curve like this, call it C. All right, so that's just a curve, it's just some subset of the plane, right? And then we could say, suppose that we parameterize it. And so we've got a function giving the x coordinate and a function giving the y coordinate as our parameter varies through some parameter domain, which in this case is the interval from a to b, right? Okay, so then the length of this curve C is going to be the integral over the parameter domain from a to b of the magnitude of the derivative, because that's speed, right? So if you look at this, if you differentiate r of t, then this is the velocity. Whoops. That's the velocity. And so if we take its magnitude, then we're looking at just the speed, because speed is magnitude of velocity. And then you know the old equation that distance is equal to speed times time. That's what it is if it's a constant speed. But if it's a variable speed, then you have to integrate that over the course of your journey. And so then that just becomes this integral that we have right here. So you can understand this arc length as just being sort of a generalization of the good old distance is speed times time formula that you learned back in, like, I don't know, grade 7 or something. So, okay, so going a little bit further into this integral that we just wrote down, this is the integral from a to b of, and so then we've got x prime squared plus y prime squared all inside the square root dt. And so I want to think about this, whoops, let me change colors, this object right here, or this object right here in more detail as dr. So this is going to be what we call the arc length element. It's going to be the infinitesimal thingy that we integrate to find arc length. You could actually think of it as distance density, but that would be crazy. Okay, so this and so this little sort of silly symbolic formula, dr is r prime dt with absolute values. You can think of as basically coming from the chain rule, right? So if r was suddenly a function r of t, what would dr be? Well, it would, by chain rule, it would burst out like this. Okay, so now this is the case for like what we do with just a curve as a subset of the plane. Now there's a special case when we have the graph of f. So if f is a single variable function, so a function from r to r, and I'll call it capital gamma G for graph, right? Because I have no imagination. So this is going to be the set of all pairs where we've got x, and then the second one is fx. And here x runs through the domain of f, whatever the domain of f is. Okay, and so if x is going this way and y is going this way, then the x coordinate is just given by x itself. And say, so here's the function that we're looking at the graph of. And so we're going from A to B here. That's our parameter domain. And we're just parametrizing this curve. So, as x goes from A to B, we're moving along this curve, all the way up. And if we stop at some moment in time, so for some particular t value right here, then with this parameterization, so we're thinking r of t is t f of t, right? Then the derivative is that velocity vector that's right there. And when we look at the components, the rate of change in the horizontal direction is going to be given by x prime of t, which is just the derivative with respect to t of t itself, which is 1, right? So in other words, I'm doing this computation right here. First coordinate is 1. And then the second coordinate, so that's how far up we've gone, that's going to be y prime of t. But y in this picture is given by f, so this is just going to be f prime of t. And so we've got f prime of t. And so that implies then that our dr is going to be the magnitude of this guy times dt, right? And so that's what you learned as the arc length element for finding the length of the curve given by the graph of a function. So in this special case, the length of the graph of f is going to be the integral from a to b square root of 1 plus f prime squared dt. Yeah?